какво е тъмната материя и как я изследваме. Съществуват ли нови частици, като аксионите, или други слабо взаимодействащи частици? Какви теоретични модели и какви експерименти строят учени от цял свят, за да отговорят на някои от най-големите неразрешени проблеми на модерната физика? На тези и на още много въпроси се опитват да отговорят учените, участващи в конференцията COSMIC WISPers Cost Action.
Тази конференция решихме да я проведем в София, тъй като всъщност българското представителство в консорциума, който се нарича COSMIC WISPers, реално този консорциум възникна покрай акция COSMIC WISPers, която успя да ни събере множество учени, на практика мисля, че над вече 300 учени от различни страни, поради това, че всъщност българското участие в самата акция и в самия консорциум е доста значимо. Ние всъщност отговаряме за една изключително важна част в тази акция и то е за разпределянето на бюджета, който се присъжда на младите учени, докторанти, постдокторанти за специализации в чужбина, краткосрочни специализации до един месец или пък за участие в конференции. И именно точно тази важна задача, за която ние отговаряме от българската страна, доведе до това, че самият консорциум реши да проведе третата международна конференция в Софийския университет и в България в частност. Ние участваме основно в един експеримент, който се провежда в Националната лаборатория в Раскати, Италия. Това е експериментът PADME, съкратено от Positron Annihilation into Dark Matter Experiment. В този експеримент ние се опитаме да изследваме прецизно взаимодействията на ускорени позитрони в фиксирана диамантена мишена, като част от тези взаимодействия могат да доведат или до раждането на тъмна материя, частици, които изграждат тъмната материя, или пък до нещо, което е още по-интересно. Преносителят на взаимодействието в сектора, изграждащ тъмната материя, който пък може да също така да свързи взаимодействието между нормалните частици и частиците, изграждащи тъмната материя. Групата от Физическия факултет всъщност беше много малка в началото, но в момента е многобройна. Тя също така и са организатори на конференцията, посветена на COSMIC WISPers, акцията, която се провежда от 9 до 12 септември в Софийския университет. Колегите, които са тук и се занимават именно с надежната работа на експеримента PADME и с изучаването на данните от експеримента PADME по един или по друг начин. Било то с методи, които са конвенционалните методи за анализ на данни, или пък с по-съвременни методи като машинно обучение и изкуствен интелект.
Dark matter is one of the big questions in science today, and there are several candidates. And I've been interested in the question how you may distinguish amongst the candidates on observational grounds, and also interested in how you may detect them on Earth, and in particular how we can detect a particular candidate called the axion. Well, the axion is a hypothetical particle. It has never been found, but it is very well motivated. It is motivated because it explains some problems in the standard model, and because it is naturally a dark matter candidate. And I actually myself believe, although people don't necessarily follow me in this, that axions have special properties in large-scale structure formation, and that there is evidence for axions in large-scale structure formation.
I'm working essentially on new particle beyond the standard model like axions and other light dark matter candidates. And I am the chair of this cost action, COSMIC WISPers, which is devoted to make searches on this new physics beyond the standard model that can answer some of the mystery of the dark universe. My main topic of research is to use stars as laboratory to probe fundamental physics, in the sense that we know that elementary particles can be produced in colliders, but so these are experiments made by men, but also stars may offer natural laboratory to probe particles with sensitivity that sometimes cannot be reached in laboratory experiments. So they can allow to extend our knowledge using these natural sources, as we have done already with the sun. So sun is our closest star, and we have learned a lot from the sun about photons and neutrinos. But now we can learn also about new particles that have not been yet discovered, like the axion, and the sun and other stars are ideal candidates to offer opportunity to study these particles.
My main interest in research is WISPs, so very light, weakly interacting dark matter candidates and new physics candidates, especially axions, but not only, and especially the astrophysics aspects of our axions. First of all, we know that there must be dark matter because it's simply a counting of energy budget of the universe. We know from many different gravitational probes that and independent probes, right? That there is not enough energy in regular matter. We need to have dark matter, and then one of the main candidates is this axion, which is a particle with it doesn't have spin, so it's a very simple properties in a sense, and it's expected to be very light, and obviously very weakly interacting. Otherwise, we would have seen it. And we expect to have a lot of axions around us, by the way. It's just a matter now of try to find it. And this is one of the things we work on right here in this community.
I try to uncover what dark matter is made of, this substance that we don't know what it's made of, but we know it's there and it keeps galaxies together. And I try to find out what it is by observing our universe with telescopes.
My research topic is partially theoretical, partially experimental, where I am working with Cherenkov telescopes that are telescopes located at La Palma, one of the Canary Islands, mainly with MAGIC telescopes, LST, and the future CTO. What I'm doing with the data that is observed with our telescopes from astrophysical objects from the space very far outside of our galaxy is that I study theoretical axion-like particles and their impact on the data, on the spectra of our sources that we are observing.
I work in a field that is theoretical astroparticle. Basically, we try to study particles, so the tiniest part of the universe, by studying how they're produced and how they affect astrophysical sources. So we study the very little with the really big structures.
We have some experiments at CERN and in the lab in Rijeka, and they space from particle physics to the dark matter and WISP stuff.
I work on theoretical physics, so which is the part of physics that gives mathematical support to experiments, and in particular I work on string theory, which is supposed to be a theory that tries to reconcile gravity in terms of general relativity with quantum mechanics. So basically the physics that describes how nature behaves at short distances. And my idea is to try to, with my research, to connect string theory with particle physics, cosmology, astrophysics, and try to get some experimental predictions out of this fundamental theory.
I'm working from the theory to experiments in dark matter particles and especially light dark matter particles. I was doing this from 2003 on. I proposed that DC should engage in such experiments, but I'm a theorist, so I had to get together with experimentalists, and nowadays we have really started a big experimental program at DAISY with different experiments for dark matter and so on.
My research is focused mainly on astrophysical probes of feebly interacting particles. So essentially we try to understand how these particles may affect standard stellar evolution, or how we can find a signal of these particles in current experiments on Earth.
I'm currently working on experimental proof of extra-dimensional physics, action physics, and possible relations with neutrino physics.
Как по-конкретно акцията помага за привличането на млади учени в областта?
Акцията дава възможност на отделните студенти, докторанти и постдокторанти да се свържат с експертите в областта, да научат от тях, да съберат информация къде какво се прави, да се изберат конкретни области, за които им е интересно те да продължат своята работа, и именно точно заради това са тези конференции, които организираме, които ако човек погледне реално профилът на присъстващите, ще забележи, че една немалка част именно са млади учени. Около 30-40 до 50% обикновено на тези конференции са млади учени, защото те са тези, които работят, получават резултатите и съответно ги представят пред научната общност.
Cost action is aimed mostly to fulfill this task, so attracting new people and a new research group. So we try to fulfill these goals organizing different activities. In particular, we have a training school. We organized already 2 training schools, and the next one will be next week in France, in Nancy. And these are aimed to allow new researchers interested in the field to learn about the development of the field by experts on different topics, and so they can reinforce their knowledge and be prepared to be the new leaders of the fields. And we also try to connect with the new young groups that are interested in entering this game, for example, organizing this workshop. So, for example, this year we are having here in this very beautiful place.
As a woman in physics, I would be very happy to see more women in our field. So, for example, we could do that by going to school and encouraging women to enroll in physics or any other hard science at the university so other women that are already in physics to go there and show that it's not only men, because some people may be put off by this.
I think a good way to do that is via outreach activities. And for example, this is part of this cost action that we do it a lot. I do it every year. I go to high school and I give outreach talks to high school students. And I always see that in this way they get passionate about questions related to the mysteries of fundamental physics, our universe. They get excited, and then most of them tell me afterwards that because of these talks they got inspired and they enrolled in scientific subjects at the university.
Children are often very interested in space and all the mysteries in space. So I think we should try to start from young age, introducing some subjects in school, and with, of course, outreach activities where we can organize, and we do organize activities of different workshops where they can learn more about the things that we do and slowly get introduced to the science that we are doing.
I mean, first of all, obviously doing outreach in schools and also opening academia to younger people. So also maybe using their communication skills by social media, videos or TikToks.
You have to make them curious and to make them see a perspective in the future.
I think the most important is to convey that it's really a lot of fun to work on these things, and that one has to of course we have to do these things full-heartedly. So it's not just a job. So I have no work-life balance. My work is my life.
I think that using social media to do outreach is very important, so that you can approach as many people as possible, and also public tools are also very important, because in this way you can involve many people and start discussing with them, and they can start be interested in what you do.
Yeah, totally agree. Like outreach events are super important. Too many people are just traumatized at school by hard mathematics, and they stop seeing what's the beauty of physics is about. So you should definitely show more often enthusiastic physicists talking about that.
Какво мислите, ще бъде следващото голямо откритие във физиката?
Много ми се ще да мога да дам отговор на този въпрос. За съжаление, нямам си никаква идея какво ще бъде следващото голямо откритие в физиката. Надявам се да е такова, което ще ни изненада включително и нас учените. Естествено, аз се надявам следващото голямо откритие във физика да бъде разбирането на тъмната материя или експеримента Падме, по който аз работя, да открие частицата, за която се надяваме или търсим, тъмният фотон или друга такава лека частица, защото нали, това е би било едно голямо постижение, но всъщност откритията във физиката не идват тук така от днес за утре до други ден, а всъщност те са продукт на изключително дълга, упорита и целенасочена работа. Така че следващото голямо постижение за мен би било да се убедят повече хора, че не моментните, т.е. революции са това, което променя физиката, а всъщност работата, упоритата и постепенното натрупване на знание и преосмисленето на тези знания води до напредък, който оттам нататък може да бъде използваем и всъщност това е прогреса в науката.
We are now in a period in which in few years new experiments will start, and so there is a chance to discover something of new that can really produce a revolution in our understanding of fundamental physics. So I think these are exciting times and we all have to be prepared and ready to have something of new that can happen at any time.
Nobody knows, but I hope we will find out what dark matter is in the next 10 years.
I would say that with the expectation of the future observatories that we are currently building and will soon start operating, we are hoping to observe very nice new phenomena from the space, like some nice, let's say maybe explosions of the in a sense of sources that we can observe, through which we can study the most amazing phenomena and things that are happening in our universe, and in that way also learn more about the Earth and the space we are living in.
I'm not really sure what will be the next, but I hope to see the next supernova, so maybe the next supernova.
I think in the next 10 or 20 years, maybe or probably we will know much more about the dark matter than we know today.
Evidence which is not gravitational evidence, so non-gravitational evidence of dark matter would be a breakthrough in all physics in general. It's one of the major puzzles that we have now. So in a sense, we can say that we detected dark matter in a sense that which gravitational, we have a lot of evidence for it. But understanding some of their properties, which are not strictly gravitational, right? Everything interacts gravitationally. So understanding, for example, their spin, their mass, if they behave like waves or they behave like matter or things like that, this would be a great breakthrough. And it will also force a lot of direct, the next research efforts toward, understanding them better, do other experiments. It would be fantastic, I think.
That's very hard to say. So we should be open-minded. But, this cost action is mainly focused on understanding the properties of a potential new particle, which is called axion. And so discovering this kind of particle would be, I think, a major breakthrough, especially from the point of view of fundamental physics like string theory, because this particle is naturally predicted by the consistency of this fundamental theory.
We don't know what the dark matter is. We are looking for the dark matter. I hope that in the next 10 years or so, the dark matter particle will be found. We have now so many experiments working in different mass regions, and at any time next week there can be an announcement of the discovery of dark matter.
Well, when you ask a physicist what is the next major breakthrough, is likely or she's likely to say recognition of whatever they've been thinking all along. So I would like to think that's happening. So I think a breakthrough could be that actions are recognized to have these special properties. But I think what would be particularly amazing is to detect them in the laboratory, because that will open a whole new window on the history of the universe, new way to look at the universe.
I hope that the next breakthrough could be the detection of dark matter signals somewhere. So maybe, we know that it exists, but we have never measured mass or found any signal beside the gravitational ones. So I think that would be a really major breakthrough. Or maybe another one, since I work with astrophysical probes, maybe the explosion of a supernova, which will be very interesting also. So. Tell us more what you are doing here in these days.
Okay, here in these days I'm helping with the organization of this great event, which is the third general meeting of the Cost Action COSMIC WISPers. So my main job here around is really to do various stuff about the organization of the event. But besides the event, I also work with real physics. Actually, I also work on the Padma experiment. And my tasks are reconstruction of data from the second run of the experiment, which searches for a dark photon, a hypothetical boson connecting the dark and the visible sector. And I also develop machine learning methods, or artificial intelligence, in order to reconstruct these events. So this is the main thing I do.
And what about you?
Same as Kalina, these days we are making our best to make you feel good and welcomed at the conference. And on the other hand, in my PhD, I'm also trying to analyze the data from round 2 and 3 of Padma.
Okay, thank you. I think that this conference is a really great success.
Yeah, you're doing a great job, both conference and physics-wise. Fantastic. So today, in these days, there are only, scientists and so on, but perhaps it would be nice to have also people from outside that understand what we do. So what do you think is the best way to get to more people understand what we do?
Actually, getting more people to understand what we do is crucial, because nowadays many people think that science is something very abstract, very complicated, and not for them. So I believe that getting the public, especially young people and students, to participate in any form of scientific things is important to show them that it's not only abstract equations and so on, but also it's everyday life. Everything that we do, and it seems very complicated to everyone, it's actually in our everyday life. So that's why I think it's very important to go to schools, to organize many public events, and of course to have these international networks like this Cost Action, so that we bring people together and that we can make science more understandable for everyone.
Oh, and I heard there's going to be a fantastic public talk today, so let's see. What do you think?
Yes, that's true. So we do a lot of things that are connected with outreach and these kind of activities. We go to schools and organize different kinds of workshops and public lectures, so that people and many students in the school can see that physics is not just this hard mathematics and formulas and so on, but it's really an amazing thing and can be very, very interesting. And there is also a lot of things to be discovered. So we need young people.
Wise words, wise words. So do you have any other question, Pep?
Well, related to this last thing that she said, so many things to be discovered. So what is the next major breakthrough in this field?
I hope dark matter, of course, because I work on dark matter. But okay, I cannot really say which of all of the possible explanations for dark matter I dream of being proven and so on. So my dream is really to see all of the puzzles that we have explained one way or another. Might not be the way I'm working on, but as long as we move forward on this, it will be great.
It's really, really hard to say, but what I can say for sure is that I'm very excited to see.